Crosstalk, Module 4.5. In this module, we will look at electromagnetic field interaction with small electrical circuits. What we will see is approximate model for differential mode noise pickup by component leads, PCB tracks and connecting wires. The assumptions are that transmission line model is valid and incident field can be approximated as a uniform plane wave or in the far field of dipoles. So we are not talking of near field coupling in this, even though, as you will see, the model that we come up is quite similar to the model that we have derived for near field inductive and capacitive coupling. But in this case, it will be action of magnetic field and electric field. Previously, we have seen that we can find maximum radiated field from electric dipole and magnetic loop, and maximum radiation is on a plane perpendicular to the dipole, and here the maximum radiation for a loop is in the plane of the loop. However, in the near field, maximum couplings are along the dipole length and perpendicular to the loop. So the problem that we have is somewhat different from the previous one. So here assume that you have two wires. It can be component lead or PCB tracks with some loads at the end, and you have a TEM wave incident, transverse electromagnetic wave, in which electric field and magnetic field are in a plane perpendicular to the direction of propagation. Now the coordinate system is defined here, x-axis, y-axis and z coming out of the paper. So since it is TEM, we can separate the effect of magnetic field and electric field, then combine those effects by applying the superposition theorem. Now let us see the inductive coupling and Faraday's laws that we have seen before, where we found that EMF by the action of a magnetic field is given by the closed line integral of E dot dl. And from this we have come up with a model for magnetic field interaction as a series voltage source. However, in representing this model, we use the circuit parameter M because we are in the near field. So we are talking of mutual inductance and all. Whereas in the problem that we have now, we will be replacing the magnetic field created by this current I1 by the magnetic field component of the wave, of the TEM wave, and we will not be using the circuit parameter M. Similarly, for capacitive coupling and using Gauss law, we found that the surface integral of the total flux coming out is equal to the charge enclosed, and from there and from the definition of capacitance we have come up with a model for electric field interaction as a current injection. However, here we will not use this coupling capacitance. Instead we will use the electric field component of the wave for finding the model. So this is just a recap of what we have seen before for the near field. So the strategy is again to model the magnetic field interaction by a voltage source, but without involving the mutual inductance, and modeling the electric field interaction by a current source, but without involving the coupling capacitors. And as before, CR and LS, series inductance and parallel capacitance, can be neglected when these conditions are true, when the impedance compared to the end impedance are meeting certain criteria. And also we will not use near field and far field anymore, because it will not make any sense. There is no near end and far end in the problem that we are investigating now. So this is the development of the model. So you have a small component lead or transmission line with some loads. So the incident wave, and it is separated by a distance s. So it is in the y direction, y equals 0 and small s. So let the magnetic field be going into the plane of the paper, incident field. So that will be equal to, because of this coordinate system, minus hz component. And incident electric field is in the y direction, the transverse field. So the normal component of the magnetic field, you take a small section of the line delta x. This is the x coordinate. So a small section of delta x. So you have an area enclosed. So the magnetic field is going through this area. So this will create a voltage from Faraday's law. So that voltage will drive a current in such a way that it should create a flux opposite to this. So the direction of the voltage source is like this. So this voltage source we write as, if Vs is per unit length induced EMF, then we multiply it by delta x, because it is proportional to this delta x. So Vs delta x is a small elemental voltage source. Total surface area is given by the small s by delta x. So similarly, electric field interaction can be modeled like this. Suppose due to this action you have a charge separation, and integral of this electric field will give you a voltage difference. Now this voltage difference is in series with this circuit capacitance. These are not coupling capacitance, so it is the capacitance between these two lines. So that can be converted into a current source, Is per unit length, and multiplied by delta x, you will get this elemental current source. So this is the model for electric field interaction. So we will find how we can find this Is and Vx in the later view graph. So the magnetic field induces an EMF, a series voltage source. So surface integral of rate of change of the flux. So if we take this small elemental area and integrate along this area, you get an expression like this. Bn is the incident flux density, and integrating over that small surface area, you can get it as delta x into small s if h is uniform across, but otherwise we can explicitly write it as an integral form. So j omega mu 0 surface integral of h ds now ds is equal to delta x into delta y in this direction. So we are assuming that the field is not uniform here. So we are taking a generic case, that's why we are doing this integral. So delta x, then as y equal to 0 to s, you are integrating h across y. So this will be equal to a voltage times delta x. So j omega mu 0 integral 0 to s h dy is the voltage source. Then delta x. Now electric field induced currents, that will be the parallel current source. So that is given by, so C times rate of change of voltage. So it is this equations we are writing. So instead of coupling capacitance, it is this capacitance that we have here. So that is the only difference. So it is quite similar, even though an important difference is that this C here is the capacitance between these two wires and not the coupling capacitance as in the previous case. So since this is positive and this is negative, but we assume the direction of the current upward, we put a negative sign in front. So this completes our model, C delta x, L delta x, and the sources. Similarly, you can have several elements like that. So in each of this element, Vs and Is can be slightly different depending upon how the voltage and current is varying along the line. So this is the generic case. Then we can apply Kirchhoff's voltage law and Kirchhoff's current law, and dividing with delta x and delta x tending to 0, you get the differential forms. And this is what is called telegraph's equations. We can derive this from this equivalent circuit. So however, we are mostly interested in what happens at the two ends rather than what happens in between. So we take a very specific case of a short line. That is what mostly we will be dealing with. And short line will be in which the length of the line is a fraction of a wavelength. So we can neglect all the variation of the field along this small transmission line in that case. So the whole width S is eliminated and there is no variation. So you can replace this integral by area A, which is given by the length of the line L times the width of the line S. So voltage source is given by j omega mu 0 area times Hn. So this will give the mu 0 Hn will be giving you the complete flux, and j omega and this flux phi will give you rate of change of flux in time domain. Similarly, the current, shunt current is L, total length, times j omega C into integral of 0 to s Ey dy. So since Ey is uniform, you replace this by L times s, small s, for the width of the line. Then you get A here, and C, A equal to L times S. So we got the values of both sources. So as before, if we say that omega L is far less than the terminal impedances and 1 by omega C is far greater than the terminal impedances, we can neglect those capacitance and inductance. And now we have just two sources, one representing magnetic field interaction and other electric field interaction, and the two loads over there. And we are interested in Vs, voltage across this, and voltage across this. So we solve for Vs. That will be, we can apply superposition theorem. First, this source. So total current is this voltage divided by sum of these currents. This voltage divided by sum of the resistances multiplied by Rs will give you this voltage due to this source. Now from the other source, where the current is divided across, current through this branch is RL divided by Rs plus RL. Then the source minus j omega Ca Ey multiplied by Rs to give this voltage. Similarly, on this side, this will be negative and this will remain the same. So as before, you can see that for the part related to electric field, on both ends the induced EMF is the same, whereas here it is of opposite direction and of different value, that from the magnetic field. So the general behavior is very similar to the near field crosstalk in terms of characteristic of the voltages at both ends. So that is end of that module. Thank you.